Okay, next up we have Vincent talking. So Vincent is a familiar face around the DeSci ecosystem. I'm sure many of you will recognize him. He used to work for Molecule, still does in a very reduced capacity, but he has moved on to start his own startup called Prime Intellect. Which is about compute power, as far as I understand, but he's going to explain it more.
Thank you. Perfect, yeah. So for those that don't know me, I'm Vincent, and I basically helped initially start VitaDAO and then also joined Molecule to help on ecosystem efforts and some product-related things. And yeah, now I started a company called Prime Intellect, and really the high-level goal is to commoditize compute and intelligence, and basically making compute power much more accessible, also with a theory that like it will be quite foundational, as well as also introducing novel, almost like business models for open source AI models. So the talk today is a bit about like how kind of like scientific progress might, like to an extent, like increasingly be driven by AI, and also what role decentralization can play, and kind of like naturally also almost like what the drivers are that drive like AI into like a decentralized and open context. Yeah, so I'll talk initially a bit like kind of like our broader vision with Prime Intellect is really broadly to make compute more accessible, as I said, and also create like incentives for people to contribute to openly accessible intelligence. And more broadly, really, because I think it's also like one of the most concrete ways how we can advance not only scientific progress, but also in general, like I think it will be quite foundational to have like universal access to intelligence that is potentially more powerful than your own. Because I think otherwise, like we run the risk to an extent to be what like maybe like animals in our current world that is like run by humans. So I think it will be quite important that it's like collectively owned and governed. Yeah, so like obviously you might have seen this chart on the left. Like I would basically make the thesis that like to an extent scientific progress is like a key driver of more general progress. Like I think the reason for why like progress across basically every relevant metric I think is driven by like progress in science, by progress in engineering and related domains. And I think the thesis of this talk, and I'll go into more depth, is that like this will be mainly in the future driven by AI, and to an extent like accelerated by AI. And obviously you also on the right like know kind of like the scientific method, and I think it's useful to almost like visualize like which of those things AI can already help with, and then also might fully take over in short time. Yeah, and I'll go into more of that. And like maybe as a starting point, I'm not sure how many of you have heard about the scaling hypothesis. Maybe raise your hand if you've heard about it. Okay, it's like a few people, but not so many. So basically, it's this biggest lesson that can be read from 70 years of AI research. It's basically that generally methods that leverage computation are ultimately the most effective and by a large margin to increase intelligence. And you see this on the right. It looks actually much small, like it looks like it's not that exponential, but it actually kind of like on this axis, like in the middle, like it's basically GPT-2, which was around about like $20,000–$30,000 of compute. Like GPT-4, for example, for context, is 200–300 million. So like that's like orders of magnitude, and already kind of like the big like CEOs of AI companies said this will scale to 1 billion, then to 5, then to 10 billion, then to 50 billion, probably equal out at like 50 billion, but like that's quite a jump from $20,000. Like, and it's not only that we jump from like $20,000 for like a model like GPT to $50 billion, but actually also in the meantime you get much more compute actually for the 50 billion than you got for the $20,000 per dollar. So it's basically like a double exponential to an extent of like scaling this compute, and my theory is like to an extent, which I think sounds crazy today, but like which is interesting like metric. It's like right now like 0.1% of like GDP is compute. I think it's quite plausible it will become 1% and 5% and 10 and then probably 99. Like and it sounds completely crazy, but I think like if one takes it seriously, I think it won't be so crazy anymore at some point, because if you literally have every car run by autonomous like agents, if you literally have science be mainly done by that, entertainment, like every area of life basically, then there's literally no limits to how much you can like leverage computation for scientific progress in every other area of life. Yeah, and this basically observation is by the inventor of reinforcement learning, who was one of the key scientists at DeepMind. So it's basically also the thesis that like the big companies like Google, OpenAI, DeepMind have, and why they succeeded also in recent years so much. And this is like an interesting website called Epoch AI on these trends. So basically, you can see that there's like 4x growth rate every year in the amount of training compute. So like every year there's like 4x more compute being spent for models, like for the big models. But there's also like actually not that many algorithmic improvements. It's not like I think it's like a declining rate in the physical compute requirement. So like there's some also algorithmic improvements, but they're actually quite shallow. Like ultimately, GPT-2's architecture is not that different from GPT-3 or 4, which is surprising to a lot of people. But then also compute got more performant. Yeah. And I think one interesting context of this is like this graph, which is compute used for scientific models. So this is also scaling up. And it's scaling up like orders of magnitude less still. So the biggest scientific models are still only like 10 million, like not 200 million. And actually, like this interesting thing is like this blue area is like the area where you need to now to follow the executive order by Biden and report on your model. So basically, you already have to report to the president at like a $10 million training run, which soon is only like a $2 million training run. So basically, already like the scaling laws for scientific models also run into, to an extent, regulation, mainly due to worries for like bio threats, etc. But it's relevant to understand because scientific models are like 2 orders of magnitude higher governed. So basically, if you spend like 20 million on a scientific model, you already have to report on this. If you spend 200 million on a general model, you don't. So it's basically scientists fall under much stricter regulations, which probably will also to an extent hold back scientific progress, maybe also some risks, but obviously also some benefits. So it's worth for the scientific community to like understand and probably to an extent even lobby for like better regulation frameworks. And I think like one interesting framework to think about kind of like progress in the future is this blog post by one of the folks from OpenAI, which is called GPT 2030. And the point of the blog post is to extrapolate like what could general purpose transformer models like large language models and agents be capable of right about by like 2030 if you scale them further. You can find the article actually if you Google GPT 2030. It's quite interesting. And the main premise, and I think it's actually to an extent pessimistic, like he's almost like lowballing it a bit, is that it will be superhuman at every task from like coding, hacking, math to protein design and a bunch of other scientifically relevant domains. And that's like in 5 years, like or 6 years. I think like if you ask some people in the field, they say it's in 2 years. Like superhuman at coding, superhuman at protein design and a lot of other relevant tasks for science. That's like fairly like in due time. Like I think even if people are pessimistic, like then it might happen in like 7 years or something, but like not never. Like so we're quite close to it that it already becomes quite relevant for science. And like I can recommend this piece without going into too much detail now, but like it's quite relevant because it also touches on a lot of scientific aspects of AI progress. And like one interesting intuition to build maybe for also like what will be relevant for science, and an interesting chat also with one of the authors of this recently, is like how also these models are evolving. So this is one project by DeepMind, and it's basically, you can visualize it as a language model, but it's running more stronger reasoning and planning. So it's a bit like you have probably heard of AlphaGo and some of the DeepMind breakthroughs on Go on these games that became superhuman, and they mainly achieved that by almost running like reinforcement learning and a lot of like planning and reasoning. And there's now basically that's like rumored to be the next wave of progress, like basically behind the next generation of like OpenAI and Gemini models is basically applying much more of this like reasoning and scaling up basically compute to basically run through all possibilities. And the interesting example with this project is basically Google was running a language model like ChatGPT and was able to make novel math discoveries with it. And it's literally a language model. It's not even like programmed to do math, but just by applying reasoning. So basically they gave it feedback like, hey, is this a novel theorem? Yes, no. Like, is this a proper solution? So it was actually able to solve like very hard mathematical problems that like no one in the world could solve until now with a language model. So not with a even math model, but with a general model, which obviously is like one relevant aspect. And that's the intuition, like when I chatted with some of those researchers, they have like for every area of science, it's like when you basically have a feedback like a mechanism and ground truth data like in math, it's very easy to get to the solution. So there's basically now the race is to an extent to find the right reward functions for science to just like brute force solutions. And the theory is like when I chatted to a bunch of people, it's like that increasingly there's more and more obviously simulations like AlphaFold is one that I'll also touch on for protein design to basically simulate science to then brute force solutions in a way that like humans wouldn't be able to. Yeah, so the implications like from this are kind of like for math, for example, is that like math will probably be solved like to an extent in every theorem that could be proved will be proven, every theorem will be basically stated. Like I don't want to give timelines, but probably fairly soon. And like it will basically automate significant portions of math, and obviously math is kind of like underlying a lot of other sciences like physics. So it's like kind of like moving up the stack, like to physics. Biology is obviously way harder, and so it's only approximating probably some of those domains like biology, while it's actually to an extent more able to brute force, say, mathematics. What obviously is kind of like this meta progress is like actually machine learning research itself, increasingly being done by AIs, but also, for example, semiconductor design, materials design that, like NVIDIA is already improving the chips mainly through AI. Like they mainly apply AI to make them more efficient to discover novel materials or drive further like improvements on their compilers, for example. Yeah, so on biology it's a bit harder, but like it's also starting to happen. And two good examples of this, of two scientific models, like you've probably heard of AlphaFold, like they also released a new update recently. And that I think is like obviously one of the most impressive models that is really good at predicting the structure of interactions of molecules. But then what's also really interesting and came out recently is another model similar to this called EVO by Arc Institute, which is also worth following, which really is like also kind of like between the interactions between DNA, RNA, and proteins. Like it basically is able to do novel things more like with a language architecture, while AlphaFold is mainly like with proteins. So there's basically like probably now like when I tracked it like a few hundred really good scientific foundation models. So across every area of science, you have a lot of models. Some of them obviously are much more scaled, but one key intuition is most of them are like have $25,000, like $50,000 of compute spent on them. Not like 10 billion or 25 billion. So my intuition is like to an extent that like the future generations will become more like general scientific models where there will be good reasons to also throw billions of compute into them to scale them up basically further. So the scaling laws haven't been like basically tried yet for science, but they do hold. Like AlphaFold got better also through scaling. So basically there's still a lot of low-hanging fruit, but just throwing more compute at all of these scientific foundation models doesn't work for all domains, but like in some domains where you also have enough data, like which is also obviously necessary. Yes, so I touched on AlphaFold, and because I'm running out of time, like and Evo, like I can recommend you to check those out. They're freely available. And maybe like as a bridge, I think they're only kind of like tools. And obviously what becomes more interesting is like with this scientific method on the right is scientific AI agents. And basically on the left you see kind of like a rough architecture of this where there's obviously kind of tools and tool use. Like it could use all of these scientific models, but it could also obviously store the knowledge, like has memory, and it can do planning. Like I mentioned with this earlier example of fun search. Basically, everything we do that like has interesting outcomes obviously is connected to an extent with planning and like reflecting on it, and then obviously can act out these things. And I think like if one understands this architecture on the left, it maps quite well also to the scientific method. Like each of those things, I think, can slowly be done by AI, and I think like obviously some of them are much harder. But a good example of this, which I'll touch on, is actually some of the already concrete examples of this. And what it needs to an extent is obviously this kind of like architecture and compute, but also some reward function, right? Like it needs to know what is it optimizing for. That's also where DeSci will come in. But basically one example worth checking out is Future House. It's funded by the former Google CEO. Big effort to basically fully automate science. And what they do is like they basically not only create AI models, but they also create physical labs that are fully automated that then can run these feedback loops. And like when I chatted with their team, but also, for example, with folks like RetroBio, which is Sam Altman's like big longevity investment. Like they're already starting to do this. Like they're literally using like GPT-4 in their like automation. Obviously, it's still very rudimentary, but like they're starting to go there, and like it took longer than people expected. Like for example, with Cloud Labs, but I think it's slowly starting to happen. And the whole goal is obviously to run these closed-loop discovery, like to really scale up science. Like for example, you could pipette as much as a human could in their lifetime overnight. Like you just paralyze, you have a cloud lab, it's pipetting much more accurately than you, much faster than you, and you don't need to do it anymore, so you basically level up. Like now you have like superhuman pipetting machine or superhuman reasoning engine or superhuman like hypothesis generation tool. So I think the interesting thing is like scientists can like level up to grander challenges than pipetting, for example. And as I mentioned, like I think the interesting thing how this maps to DeSci is, to an extent, you need these reward functions. And like what are the best reward functions in the world to an extent is like dollars for something. And I think that's what crypto is all about. It's like designing kind of reward functions. It's like designing crypto economic incentives. And Vitalik had this interesting blog post on some like how crypto and AI overlap. And like he had these categories, for example, as like crypto as a reward function, or AI as a player in a game, maximizing a reward function, for example. And I think that's what's going to happen. And like to illustrate this example, I've picked the example of like a BioDAO, which to an extent can be viewed as an environment, because like an agent can start to make a proposal, it can get rewards, it can, and you kind of like don't even know, to be honest, like on some folks, if they could be a machine, like they could have a name like a human, but like they have the 0x identifier, they have the username, you've never met them, right? So I think it's actually an interesting environment for machines to come into, obviously on different functions of it. And I think increasingly over the very long term, I think it's interesting to think about like what will be the last thing that humans have left, like right, like and the last thing for humans to do is to an extent capital allocation. Like you're a state, right? You have trillions, and you're like, hey, which department to give it to, which company or which agent? And I think DeSci and these DAOs, like they'll have money, and the main function is to an extent capital allocation. So they're kind of ready for an age where science is like decentralized and autonomous and yeah, done by machines. It's literally in the name. So I think it's like there's ways to basically move in that direction. But because I'm running out of time, like I'll basically run through quickly like a summary. So like I think the key that I want to convey is like I don't know if it happens in a year or 2 or 5, and that's kind of not the point. Like obviously progress is happening always, and especially recently starting to become more exponential. And I think the interesting thing is like how the overlap between basically AI, decentralized AI and science could look like is that decentralized organizations like leverage compute and AI agents and novel incentives to really make science much faster and collaborative and accessible, because like everyone in the world can contribute. Ultimately, I think it's still important that humans are involved in some capacity. Otherwise, like it could become a bit risky, like if they're completely out of the loop, which I think is also plausible that they will be, because at some point if a machine writes 10 million lines of codes per second, like it's hard to overlook that, like it's hard to debug that. It's just like superhuman at code writing and much faster, obviously. So, and I think it will be similar for science. Like if it pipettes like 10 trillion pipettes per second, like how do you overlook that, right? Like you kind of then need to overlook the AI that overlooks this process. So I think like there needs to be also mechanisms to basically slowly grow into this. But I think, yeah, like this key like aspect how science could look like if there would be pretty exponential AI progress, would be that basically DeSci's main function will be like a capital allocator, which I think cryptos is to an extent, where people decide like, hey, which areas of science do I care about, and where do I put my money, which basically is also compute, where do I put it into? So basically I think that will be one of the core like long-term trajectories like for decentralized science. Yeah, so that's about it. Like I'm happy to take questions if there's still time and explore collaborating and supporting the organization. Didn't touch too much on like what we're doing, but like we're, among other things, providing like cheap compute and funding scientific foundation models. So we're basically like quite directly involved in a lot of those things. Yeah, and excited to explore collaboration with some of you. Thanks.